So stellar evolution is just what we call the life cycle of a star. And here I've included one of my favorite Hubble images. This one is of the quintuplet star cluster. And I really like this one because you can really clearly see that stars come in a lot of different colors based on luminosity and temperature. But stellar evolution is just essentially the life cycle of a star. It just makes more sense to call it stellar evolution because, like, a life cycle is weird to refer to something that isn't actually alive. And so this is the HR diagram, the Hertzsprung-Russell diagram. And this is really important because it helps us classify stars. So the vertical axis here is in units of luminosity. So we start with low luminosity at the bottom to high luminosity at the top. Luminosity is a measure of the absolute brightness of a star. So what we typically perceive here on Earth is brightness. So when you look at the night sky, the stars that are brighter, and there's stars that are dimmer. That's brightness. Brightness, however, is not a good measure of a star because it's not always intrinsically related to what the star is. For example, a star can look really bright in the sky because it is, a really bright luminous star, or it can look bright in the sky because it's really close to us. So luminosity is basically adjusting for that difference in distance. So it's the absolute brightness of the star, or it's a absolute measure of like the energy that it's producing. The horizontal axis here is in temperature, and it's kind of weird because the highest temperature is back here in the dark blue colors, and then the lowest temperature is over here with the red. So first off, we have stars that have high luminosity. So that's these guys way up here, and those are our supergiant stars. Supergiant stars are some of the most luminous stars in the universe. We also have stars that have like low temperature and low luminosity. So this kind of patch of stars down here in this part of the diagram, those are our white dwarfs. They've got lower temperatures and much, much lower luminosities. So they are quite dim compared to a supergiant star. And lastly, we have these stars that have this really strong correlation between luminosity and temperature, where essentially we're saying the higher their temperature, the more luminous they are. And the lower the temperature, the less luminous they are. And this is a very important stretch of the Hertzsprung-Russell diagram that we call the main sequence. So we see we have these stars that almost form this nice, perfect straight line, where ones down here at the bottom have a low temperature and a low luminosity, and those ones up on the top have a high temperature and a high luminosity. And most of a star's lifespan is set as a main sequence star. And we'll talk about that as we kind of get into the different stages of stellar evolution. But those are kind of like the big sections of the Hertzsprung-Russell diagram. And we're going to see this diagram a lot as we talk about stars. So first off, we've got star creation. Star creation occurs in stellar nebulas. So basically areas where you've got a lot of dust and gas that stars can be made out of. This right here is a picture of the star forming region of NGC 2074. So the first stage in a star's life cycle is the protostar. And so this is basically everything that's got to go on before it becomes an official star and nuclear fusion begins. So in the stellar nebula, there is all of this gas and dust. And this gas and dust tends to start to clump together due to gravitational attraction. So the gas is attracted to each other and it starts to collect into this big ball. The bigger the amount of gas that accumulates, the more pressure that happens. And so this gas starts to collapse in on itself due to gravity. So when you've got a lot of gas, like the gravitational attraction wants to pull it all in together. However, another thing that we know about gases, though, is that gases want to spread out as much as possible. Think about a balloon. So in a star, you have gravitational force pulling the gas inward, collapsing it inward, but the gas itself is still exerting an outward pressure. And so there tends to be kind of like a balance between this. At some point, though, because of the gas collapsing in on itself, temperature and pressure will get very, very high. They will continue to rise, and once temperature and pressure has gotten high enough, then nuclear fusion will begin. And that's when the star is born. It becomes an official full-fledged star rather than a protostar. So here's kind of a diagram that we can kind of think of it. Like step one for a protostar is you start to have gas collapsed by gravity. So the gas starts to get collected together in this big ball here. And then the internal temperature and pressure starts to rise again as the gas is getting compressed more and more by gravitational force. And then once temperature and pressure is high enough, nuclear fusion will begin. So all stars have this kind of interplay between outward pressure from radiation and just the gas wanting to spread out, and then this inward compressing pressure of gravity wanting to pull everything together. So next up, a fully developed star, something similar to our sun, will fall on the main sequence. And again, like I said before, this is where stars spend most of their life cycle, is on the main sequence. You probably can't see it from back there, but our sun is kind of almost right in the middle of the main sequence here with these other yellow stars. And then what kind of happens after a star it kind of ages away from the main sequence really depends on its mass. So low mass stars tend to take one path and high mass stars tend to take another. We're going to first talk about low mass stars because our sun is an example of a low mass star. So we're going to kind of look at the stages that our sun will eventually go through. So as the sun or any low mass star ages, it's going to become a red giant. So basically at some point, as more and more of its hydrogen fuel gets converted into helium, its temperature is going to drop because less fusion is taking place in the core. And as a part of that, drop in temperature, the star itself also expands. So it gets cooler and it gets literally larger in size. So like here, this is kind of like if we were comparing like a star similar to our sun, this would be like its normal size when it's on the main sequence. And then this is what it's like when it expands to become a red giant star. And part of this process of becoming a red giant is cyclical. And so that's where variable stars come into play. As part of this aging process, the star will expand for a while, and then it'll contract again. And then it'll expand again, and it'll contract. And it can do this over a period of days. So most variable stars have like dimming, and part of this expansion and contraction actually causes them to dim and brighten. And so this can happen over a period of 1 to like 70 days, which is really quick for a star. So I want to kind of show us this video so we can kind of see what that looks like. So it's going to zoom in and actually highlight what the variable stars are. And so we should be able to actually notice and see them getting slightly dimmer and brighter. So it almost looks like they're flickering, right? They're getting bright and then dimmer, just a little bit. And they're going to show us actually several types of variable stars, because again, a lot of these things are subdivided into different categories based on their properties like temperature, luminosity, how long it takes them to dim and bright. So here they'll zoom in on even some more fainter variable stars. And here you can see like some of these bigger ones really a lot better. See it dimming and brightening. But yeah, RR Lyrae variables are very dim and hard to see. That gives us an idea of what that's like. It's not going to let me do it from there. Okay. So at some point, a star will also go through an outer shell ejection. So basically what that means is that its outer shell of hydrogen gas is going to get ejected. And all that is left behind is the core of the star. So most of its gas has been converted from hydrogen into helium. And then as we get much, much closer to the end of a star's life, the last little bits of hydrogen get ejected, and all that's left over is the core of the sun, or core of the star. And again, this is something that our sun is going to experience at some point. The hydrogen gas that's been blown off or ejected from the star is called a planetary nebula. Now, all of low-mass stars are going to go through this ejection process, but not all of them will have visible planetary nebulas. So the core of the star by itself still has to be emitting enough energy to basically interact with the particles of gas that it's ejected to cause them to glow. And then we will get a visible planetary nebula. But some stars don't produce enough energy for us to actually see their planetary nebula. But the ones that we can see are some of the arguably most beautiful objects in the universe. So in the top left is probably one of the most famous planetary nebulas, and that's the Cat's Eye Nebula, or NGC 6543. And you can kind of see why they call it Cat's Eye, because it's got that like elongated kind of pupil look to it. And then right next to the Cat's Eye Nebula is the Ring Nebula, or M57, which is one of my favorites. And then right here at the bottom, we've got the Hourglass Nebula, or MYCN 18. And then a few more nebula, because I just love nebula. They're some of the most dynamic and interesting and beautiful things. So on the left up there is the Little Gem Nebula, or NGC 6818. And then on the right over here, this is NGC 2440. And then again at the bottom, we have the Twin Jet Nebula, because the gas seems to be blown off in like two very specific directions. But with all of these, you gotta imagine that in the center is the leftover core of the star. And this is just all of that outer hydrogen gas that's been blown away. So then we get to the death of a low-mass star. And once that outer shell of hydrogen is gone, all that's left is this thin layer of helium and what tends to be a core that is mostly composed of carbon. Because again, over time, heavier and heavier elements fuse within the sun. And gravity is going to pull that remaining core of the star in even farther. And our result is a very small, very dense, relatively dim star known as a white dwarf. Again, these have a low luminosity and a low temperature. And once a star, a low-mass star, reaches the point of a white dwarf, it's just going to continue to slowly cool over time. until it's not emitting any energy anymore. At that point, again, like I said, the white dwarf will cool, it'll get even dimmer, it'll get redder, and eventually it will completely cool off and it won't be emitting any energy anymore, it won't be emitting any light, and that's where we get a black dwarf, which is essentially, it's the same thing as a white dwarf, it's cooled off and it's not emitting energy anymore. Sometimes people call these brown dwarfs, but a brown dwarf can also be used to mean something else other than a dead star. So typically I'm going to use the term black dwarf. Because a brown dwarf can also be used to refer to an object that's like not quite a gas giant planet, but not quite a star. So here's kind of like a summary of the life cycle, the stages of stellar evolution for a low mass star. So something like our sun. It starts as a protostar, spends most of its life on the main sequence. Then as it ages, it'll become a red giant. And then again, it'll go through this series of expansions and contractions as a variable star. Eventually it will eject that outer layer of gas, which will form a planetary nebula. And all that will be left behind is the core of the star, which is a white dwarf, that over billions and billions of years will eventually cool off to the point where it's not emitting any energy, and it'll be called a black dwarf then. High mass stars, on the other hand, go through a slightly different lifestyle. So high mass stars, we're talking about stars that are much, much more massive than our sun. They still start off as a protostar and spend most of their life on the main sequence. But as they start to age, they expand way, way more than a low mass star and form what we call a super red giant. It's similar to a red giant, it's just way bigger. They also tend to form variable stars. Again, this whole expansion and contraction goes on for a period of time. But when a high mass star gets to the end of its life, it doesn't just kind of eject some gas and fizzle out. It explodes in what we call a supernova, which is the most explosive event in our solar system. And what's left after a supernova explosion is a neutron star or a black hole. Again, depending on just how massive this star is. Because it's got to be really, really, really massive to collapse all the way into a black hole. So let's talk about some of these different things, specifically a supernova. Again, a supernova is just a gigantic explosion. The star literally blows up. And we get insanely high temperatures. We're looking at like 600 million Kelvin. And these super high temperatures are what cause all of the heavier elements in the universe to fuse. So, right on up to like iron. So the super high temperature can cause fusion to happen again, up until we get to iron. Iron is one of those things that doesn't matter how hot you get it, it just won't spontaneously fuse. And so that's where fusion stops. Here's kind of an example of just how bright these things get, okay? So in this image on the left, this spot right here is the star before it goes supernova. And this is what the supernova explosion looks like. Really big supernova that are closer to Earth can actually be viewed sometimes during the daylight. There's a lot of historical accounts of supernova explosions being visible during the day. Yeah?
So like, let's say the sun were to explode, would it take 8 minutes for like that to get to us and like we see it? And...
Correct. Yes. Because it takes 8 minutes roughly for light to travel from the sun to the Earth, if anything happened to the sun, yes, it would take us 8 minutes to know about it.
Really?
Yes.
Or, I mean, I guess if we had like satellites and stuff to like detect certain
I'm not
information.
sure if the satellites could get us the information any faster. Because we're assuming that the satellites are like transferring information as, you know, electromagnetic waves, probably like radio waves or microwaves,
Yeah, that's true.
which would still be traveling at the speed of light, which would still take 8 minutes probably,
That's true.
or roughly. But yeah, something like most supernova, when we see a supernova explosion in our sky, the star is long since exploded. Because these stars are like usually hundreds of thousands of light years away at the closest. So when we see a supernova explosion, it's actually the star has like exploded a really long time ago. But they are very bright. So supernova explosions can also often leave behind nebulas. So obviously when a star totally explodes, you can kind of get like a gas cloud left behind. And probably one of the most famous supernova remnants that is a nebula is the Crab Nebula. That's what this image is of right here. And the Crab Nebula was first noted in 1054 as a supernova remnant by Chinese astronomers. Chinese astronomical records are actually a really a wealth of information for astronomers, because the Chinese studied the sky and they had a very like specific date system. So like most of their records are dated really, really accurately. So if you want to like, you know, figure out if there were records of different historical astronomical events, Chinese historical ones are really good to look at because all of their dates are very precise. Now, the other thing that happens, we talked about how during the explosion itself, the star gets really, really hot. And so the atoms, including carbon, start fusing again, and they can fuse all the way up to iron. Now, all the heavier elements beyond iron in the universe are kind of formed by essentially the shock wave of the supernova. So the ejection cloud from the supernova is traveling away really, really fast. And there's all this intense heat and pressure. And it's that intense heat and pressure that forces heavy elements like iron to fuse farther. And again, that's where all the other elements in the universe come from, is from essentially the shock wave of the supernova. Which means everything in the universe that contains elements heavier than carbon, which includes us, is made from the remains of stars that have exploded. And so, as Carl Sagan very quaintly coined, we are made of star stuff. We are a way for the cosmos to know itself. As you probably have already noticed, I'm a big fan of Carl Sagan. I liked his thoughts on things. So again, after a supernova, there are usually some remains of the star, and gravity recollapses them. And what they recollapse into, again, depends on the mass. Most high mass stars will recollapse into a neutron star. So called because the only thing really that's left behind after the supernova are neutrons. And so it's this very small but also insanely dense object. And a lot of neutron stars actually emit pulses of radio waves at regular intervals. So they almost kind of like act like a lighthouse, so where we kind of pick up their little beacon or flash of radio waves every so often. And those type of neutron stars are called pulsars. And we think that a pulsar is just a really rapidly rotating neutron star. We don't need to hear the music on that, it's weird. But yeah, so this video kind of talks about, gives us a good illustration for pulsars, some of which actually are moving through our galaxy. So sometimes what we think happens is that the supernova explosion kind of gives the pulsar a little push, and so the star itself ends up moving through the galaxy. Just kind of funky to think about because we don't usually think about stars as like moving that much or that rapidly. But sometimes pulsars do. And then this is, again, another image of the Crab Nebula, which does have a pulsar at its center. So there's also some different types of pulsars. There's what's called a magnetar, which is a pulsar with an insanely intense magnetic field. So we're talking like 1,000 times stronger than what you would normally expect for a neutron star. And that's going to make it like 1 trillion times stronger than Earth's magnetic field. So some of the most strongest magnetic fields that we know of in the universe. And then of course we talked about pulsars as a type of neutron star that emits pulses of radiation. And then sometimes, though we haven't found very many of them, you get a combo where it's a magnetar and a pulsar. Now only 6 of these type of neutron stars are known at the moment, so they might be pretty rare, or it might just be that we haven't detected many of them yet. Now let's talk about black holes. If a star is really, really massive, it won't just collapse down into a neutron star. It'll keep collapsing and collapsing until you have an immense amount of mass concentrated in an infinitely small space. And that's a black hole. Now, infinitely small is kind of hard to think about. We don't usually think about anything in nature as being infinite. But according to the math, that's what a black hole is. It is a huge amount of mass crammed in an unbelievably small space. It's like a infinitely deep well in the fabric of space-time. And that's why nothing can escape from it, including light. And it's this whole idea of it being like infinitely small, which is why when the whole idea of black holes was first brought up, most people didn't actually think they existed. So black holes were first discovered as like a mathematical anomaly. Someone was working out the equations and realized that, some of the equations solved to be this weird object. But again, most people thought it was just a weird quirk of the math. It wasn't actually a real object. Until people started finding these invisible sources that were emitting huge amounts of X-rays, which matched a lot of the data for black holes. And nowadays, we even have a photograph of a black hole. The first photograph ever taken was done a couple years ago. So we have indisputable proof that they do indeed exist. So some basic things about the black hole. There is a radius around the black hole, and somewhere at that radius around the black hole is the point where light can no longer escape from the black hole. And that's called the event horizon. So the event horizon is typically larger than the black hole itself, and can vary a lot in size depending on a lot of factors. The very center of a black hole is called the singularity. And again, this is something that is only known through mathematics and prediction models, because there's no way you can see into a black hole. The very nature of a black hole means that light can't escape. So that means any kind of electromagnetic radiation will not be able to escape. So there's no way for us to send a probe to the inside of a black hole, because if its communications would never get back out again to us. The Schwarzschild radius is a theoretical radius at which a spherical body becomes a black hole. So basically, it allows us to figure out how much would you have to compress something, like how small would you have to compress something for it to collapse into a black hole. And for something like the size of our sun, you would have to collapse it so that it was only 2 miles wide. If you could compress the sun to it being only 2 miles wide, it would then collapse into a black hole. For something the size of the Earth, you'd have to compress it to the size of 1 centimeter. If you could compress the entire Earth to 1 centimeter, then it would collapse into a black hole. And that's essentially what the Schwarzschild radius allows you to calculate. This right here is a short video on the first image of a black hole that was ever taken. And it's really, it's very interesting because they do a good job of explaining what we're seeing as well as like how we got the picture, because it was a very, very difficult process that really required like global cooperation.
Black hole, released by the Event Horizon Telescope collaboration on April 10th, 2019. It shows plasma orbiting the supermassive black hole at the center of the galaxy M87. The bright region shows where plasma is coming towards us, and since it's traveling near the speed of light, it appears brighter when coming towards us and dimmer when going away. This is called relativistic beaming. From the images, scientists can tell that the plasma is orbiting clockwise. It takes around 2 days for the plasma to complete one orbit. Here, we are looking at the black hole using electromagnetic waves with a wavelength of 1.3 millimeters, radio waves. This was the part of the spectrum used to make the image because it can show us the features close in to the event horizon, and it can pass through the accretion disk and interstellar dust to reach our telescopes. The supermassive black hole in M87 is very active, meaning it's constantly feeding on lots of matter from its glowing hot accretion disk. But it also has narrow collimated jets above and below it, here shown in blue, thought to be created by incredibly strong magnetic fields. The jets extend out at least 5,000 light years, and one of them appears to be pointing almost straight at us. Relativistic beaming is again the reason we can see the jet coming towards us in this Hubble Space Telescope image, but not the one going away. Since the jet is pointed almost straight at us, I'm thinking our perspective is almost perpendicular to the accretion disk. But let's have a look at what we would see if we were looking at different orientations. The warping of space-time around the black hole means we can see light even from parts of the accretion disk behind the black hole. They are lensed above and below the shadow region. Not gonna lie, this is so trippy, I could stare at it for a long time. So the big question most people are going to be asking is, why is the image so fuzzy? The answer is, because it's so tiny. Don't get me wrong, the black hole itself is huge, supermassive, in fact. As measured from this picture, the black hole has a mass 6.5 billion times that of our sun. The actual size of its shadow is nearly the size of our solar system. But located 53.5 million light years away, its size from our perspective is only about 40 micro arcseconds. That's the angle it makes on the sky. To understand what that means, take the whole sky and divide it into 180 degrees. Then divide a degree into 60 arc minutes, and an arc minute into 60 arc seconds. Divide an arc second into 100, and into 100 again, and into 100 once more, and that is the size of the black hole shadow, only about 40 micro arc seconds. It puts us at the very limit of what we are technologically capable of seeing. In fact, to get this sort of resolution, due to the basic law of physics, the diffraction limit, we needed a telescope the size of the Earth. That being impractical, the scientists used 8 telescopes spread across the globe. They all simultaneously observed M87, and as the Earth rotated, that helped fill in the Earth-sized telescope that they were trying to simulate. But M87 was not the only black hole they looked at. They also observed the supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star. They haven't yet released an image of this black hole, but this simulation shows what it might look like. It's much closer at around 26,000 light years away, but also much smaller, with a mass only 4 million times that of our sun. It's also less active, only periodically gobbling up matter, and it would have much more variation over time, with matter orbiting every 4 to 30 minutes. That's probably why we'll have to wait a little longer to see the black hole at the center of our galaxy. For now, the striking image of the black hole in M87 confirms beyond a shadow of a doubt that black holes do exist. The general theory of relativity, published over 100 years ago, is supported again in spectacular fashion in the strongest gravities and at the limits of our ability to test the theory. What I love about moments like this is the ridiculous extreme things these scientists did, these 200 scientists, in pursuit of a goal that seemed impossible, and yet they achieved it. I want to extend my personal congratulations to everyone on the team for an amazing discovery. I'll be linking to all their work in the description.
All right, so let's do a quick review of stellar evolution here. This image up top here is the life cycle of a low-mass star, so one like the sun. And again, right now, we're about 4.5 billion years into the sun's life cycle, 4.6 billion to be precise. And over time, you know, the sun's going to expand and eventually it'll become a red giant. It'll blow off that outer layer of hydrogen gas as a planetary nebula, and then there'll be a white dwarf left behind. And very, very slowly over time, that white dwarf will cool and fizzle out. The sun is predicted to become a red giant in about another 5 billion years. So fortunately, not something we really have to worry about at the moment. This is kind of a full look at stellar evolution for low and high mass stars. And you'll see that there's a few extra things on here. Because again, like we kind of looked at the very broad strokes of this, and there's a lot more fine details that can be gotten into. But everything kind of starts out as protostars in some kind of cluster, and then it'll either form a low mass star or, again, what we call a brown dwarf if it doesn't get quite enough gas to like start nuclear fusion, which will eventually become a red dwarf or a red giant. And we talked about how it'll blow off its outer gas, the planetary nebula, white dwarf, and then eventually cool off to a black dwarf. However, sometimes the red giant doesn't just like totally blow all of its gas off. Sometimes you get this weird kind of middle thing where you've got like a red giant star that's binary with a white dwarf. And that kind of combination can lead to a couple of different things. It can lead to a nova, which is a smaller explosion on the star. So it's still an explosion, but it doesn't destroy the star. It's just kind of an explosion that happens on the surface of the star, which will again kind of eliminate the red giant in that pair, and you'll be left again with just a white dwarf. Or sometimes this red giant white dwarf binary system will have the white dwarf kind of sucking matter away from the red giant. And there will be a point when the white dwarf reaches a critical amount of mass that it has gained from its binary red dwarf, and it will explode in what we call a type 1a supernova. And type 1a supernovas are really specific because they always tend to have the same brightness. And so they're one of the things that we can use as a standard candle to look at distances in space. Again, supermassive stars will become super red giants. They'll undergo a type 2 supernova, and then there will sometimes be a supernova remnant, like a nebula, like the Crab Nebula. And then, depending on its mass, if it's less than, I think it's 40 times the, let me look at this, let me see, because I can see it better on this image. Yeah, if it's less than 40 times the mass of our sun, it's just going to collapse into a neutron star, probably be a pulsar. If it's greater than 40 times the mass of our sun, that's when it'll collapse into a black hole. And that is kind of the whole shebang with stellar evolution.